Good day. My name is Nitinol Adeeko, a WEN-HCO intern with the APC Center. This summer, I had the pleasure to work with Dr. Janet Gabor and Professor John Lewandowski, both from the Department of Material Science and Engineering here at Case Western University. And we worked on the mechanical characterization of Nitinol wires for use in orthodontics. An orthodontic archwire is one that conforms to the alveolar or the dental arch and is used in braces. It works by applying a gentle force, which helps in correcting irregularities in the position of the teeth. Because of this specific purpose, we expect the archwires are non-toxic as they'll be used in a physiological environment for extended periods of time. We also expect that these materials will not tarnish and will possess desirable mechanical properties such as a high modulus of elasticity, high formability, and high resilience, among others. Now, there are many different materials such as stainless steel and beta titanium that fit this criteria. So it is important to characterize all these appropriate materials or all the suitable materials to help clinicians decide which material is used for which stage of orthodontal treatment. Now, my research focused on nitinol, and I chose 5 different nitinol specimens that vary in dimension, cross-sectional area, and company that we sourced the specimens from. I went a step further to get legacy data from other materials like beta titanium and a similar material like nitinol superelastic, just to see how well these materials compare and how well my materials compare to legacy data. I carried out tension tests using the Instron 1130 at a test rate of 1 millimeter per minute. The gauge length I used was a 12.7 millimeter, which is equivalent to half of an inch. Based on the results obtained from my tension test, I was able to set up a flex bending fatigue test. I carried out this test using the Bell Fatigue Ductility Flex Tester at a rate of 1 Hertz and an R of -1. An R of -1 simply means a fully reversible flex bending fatigue. The mandrel sizes I chose were of diameters 19.05 millimeters and 31.80 millimeters, which was based from the result of my tension test. Now, zooming into my tension test, from my results, you can see that there's a clear ranking in the ultimate tensile strength characterized by the peak of the stress strain curves and the toughness of the nitinol wires characterized by the area under the curves. Comparing this to the legacy data, which are the gray and the black curves, we notice that titanium does not reach as high ultimate tensile strength as some of my nitinol wires and does not compare in terms of toughness with the nitinol wires. Over on my right, I obtained fractography images using the scanning electron microscopy just to understand how the modes of failures of my wires. These pictures above are characteristic images of wires with a circular cross-section, while the images below are characteristic images of those of a square cross-section. This table is a summary of the results obtained from my tension testing and my percentage reduction of area calculations. I obtained this information by using ImageJ to analyze this surface and to analyze the fracture surface and calculate the area of the reduction of area. Also, I wanted to note the small vertical lines. These are the strain levels that I calculate that I use for my flex bending fatigue that I'll talk about in a little while. This chart shows the strain amplitude versus fatigue life of my 5 nitinol wires, each of which have 2 replicates. Over the far left, you can see the gray points which represent legacy data, and you notice that they fail much quickly than any of the nitinol wire, which also helps in understanding why we characterize these materials. On my right, just as I did for the tension test, I've presented the SCM images obtained just to show the characteristics failure modes for a circular cross-section and a square cross-section. Each of these wires have an initiation point, which is clear in some cases, which is not clear in some cases, but this propagates to the fatigue region and eventually an overload region where catastrophic failure occurs. Again, I've just given a nice overview of the 5 different specimens and their fractography. Still on fractography, I noticed that there were some non-metallic inclusions and some voids that were very interesting findings. For the Nitinol superelastic in particular, the void occurred around the edge of the wire, and this served as an initiation site that further led to crack propagation and eventually failure. This is just the left half of the broken specimen, while this is the right half. This was a fatigue specimen. This same material, but under tension, did not show any voids or initiation point, but there were presence of characteristic inclusions, which eventually nucleated to form dimples, and these are characteristics of ductile failure. In conclusion, I want to note that I only carried out 1 tension test, while my fatigue test had only 2 replicates. Hence, it is difficult to make definite conclusions. However, based on the result I obtained, I noticed that mechanical properties are affected by geometric changes, and this is particularly evident between Bioforce 1 and Bioforce 2. These materials are identical with the exception of their dimensions, which Bioforce 1 being slightly bigger than Bioforce 2. However, there is a difference in the ultimate tensile strength, with the bigger one having a higher UTS, while Bioforce 2 has a higher percentage reduction of area. Other general observations that I noticed was the ranking of the ultimate tensile strength from 1,666 megapascals to 870 megapascals for Bioforce 2. Interestingly, this trend from Nitinol superelastic to Bioforce 2 was reversed for the percentage reduction of area, with Nitinol superelastic having the smallest reduction of area and Bioforce 2 having the largest reduction of area. This makes sense because there's often a trade-off of strength for ductility for wires. Finally, my SEM shows the fatigue initiation size and ductile overload as expected. And I noticed that for rectangular specimens, initiation site often occurs at or around the curved edges. If you look at these images, this makes sense because these curves are often sites of high stress concentrations. Finally, I would like to acknowledge these individuals for their contribution towards my research in providing background information upon which I built up. These are my references. Thank you.